Gravity feels like a force. You feel it pulling you down. You feel it when you jump. You feel it every time something falls. So it's natural to say, gravity is a force. And in many situations, that statement works perfectly well. But in physics, the full story is a little more subtle. Today, I want to explain what gravity really is, why it feels like a force, and why physicists sometimes say that gravity is not a force at all. Not to confuse you, but to make the picture clearer. Let's start with the version everyone learns first. In classical physics, gravity is a force. Isaac Newton described it as an attractive force between any two objects that have mass. The more mass, the stronger the attraction. The closer the objects, the stronger the force. This description is incredibly successful. It lets us calculate orbits. It lets engineers build bridges. It lets us send satellites into space. It lets airplanes fly and land safely. For everyday life, for engineering, and even for most space missions, Newton's gravity works beautifully. So why did physicists ever question it? Because when measurements became more precise, small problems began to appear. Very small ones, but real ones. One famous example is the orbit of Mercury. Its path around the Sun shifts slightly over time, in a way Newton's equations can't fully explain. Another issue appears when gravity becomes extreme, near very massive objects, near very dense objects, near objects like black holes. This is where Albert Einstein enters the picture. Einstein did not say, Newton was wrong. He said, Newton's description is incomplete. Einstein proposed a deeper explanation. Instead of describing gravity as a force, he described it as the geometry of spacetime. That sentence sounds abstract, so let's slow it down. Spacetime is not a substance. It's not a material. It's not something you can touch. It is a mathematical description of how space and time are structured together. Mass and energy change that structure, and objects move according to that structure. In Einstein's view, objects are not being pulled by gravity. They are following the straightest possible paths in a curved space-time. This is the key idea. Gravity is not something acting on objects from the outside. It is something that changes the stage on which motion happens. Imagine rolling a ball across a flat floor. It moves in a straight line. Now imagine the floor is curved. The ball's path bends, even though nothing is actively pushing it sideways. From the ball's perspective, it's just following the geometry. This is why physicists say, in general relativity, gravity is not a force. Objects in free fall are actually not being forced at all. They are moving naturally through curved space-time. And this explains something surprising. When you are falling, you feel weightless. Astronauts in orbit feel weightless. Objects in free fall feel weightless, because there is no force acting on them. So why do you feel gravity when you stand on Earth? Because the ground is pushing you upward. Your body wants to follow a curved space-time path inward. The floor prevents that motion. That resistance is what you feel as weight. In this sense, gravity is what you feel when something stops you from freely falling. Now here is the part that often causes confusion. If gravity is not a force in Einstein's theory, why does it behave like a force in everyday life? The answer is approximation. When gravity is weak and speeds are much slower than the speed of light, Einstein's equations reduce to Newton's. The geometry becomes almost flat. and motion looks exactly like a force pulling objects together. So Newton's gravity is not wrong. It is an approximation of a deeper description.
This is very common in physics. We use simpler models when they work. We use deeper models when precision matters. Electricity is similar. We talk about electric forces, but at a deeper level, they arise from fields and quantum interactions. Both descriptions are valid depending on what you're doing. So when someone says gravity is a force, they are correct in the Newtonian sense. And when someone says gravity is spacetime curvature, they are correct in the relativistic sense. These are not competing ideas, they are layers of understanding. This distinction becomes crucial near black holes. Near a black hole, spacetime is curved extremely strongly. Newton's approximation breaks down. Einstein's description becomes necessary. This is why black holes are not just strong gravity. They are regions where spacetime itself behaves very differently. Time slows, paths bend sharply, and familiar intuition stops working. But none of this means that gravity is imaginary or not real. Spacetime curvature is not a philosophical metaphor. It produces measurable effects: time dilation, gravitational lensing, orbital shifts, gravitational waves. All of these have been measured experimentally. So the most accurate statement is this: gravity behaves like a force. But at a fundamental level, it arises from the geometry of spacetime. Both statements can be true at the same time. Physics is not about choosing one description and rejecting all others. It's about using the right description for the right level of precision. Newton gives us intuition. Einstein gives us depth. And when you understand both, gravity stops being confusing. It becomes one of the most elegant ideas in science. A force you can feel, a geometry you can't see, both describing the same reality. If you want, the next step is to explore how this geometry creates black holes, why nothing escapes their event horizons, and how gravity can shape entire galaxies. Until then, subscribe for more Science in Minutes. And let me know in the comments, did gravity feel more intuitive as a force or more elegant as space-time geometry?